Okay, so I will go a little bit into details about the Gaussian mixture models now. We have a section on the theory, which I will probably not go too deep into it. And then we have a hands-on. So how are GMMs used for biometric recognition? So they are widely used for speech processing, GMMs, Gaussian mixture models, to model the speech signals. But they are mostly unknown in other biometrics, although we have shown that they actually work quite well also for face. And the basic idea is that we extract a lot of local features from a data sample. And instead of concatenating these local features into global features, we treat all these features as independent observations of the same object. For enrollment, the basic idea is that we model the distributions of these observations from enrollment samples. So we have 5 images in our data set, and we just model the distribution of the features of these 5 features, of these 5 images. And this is our model for our identity. And then when we score, we compute the probability that the features from the probe were actually generated by the model of that person. That's why we call it a generative model, generally. Although you can treat it as any other biometrics, but it's called a generative model. Local features typically are, so for speech signals, you can extract like MFCC features, which are extracted from like local parts of the speech signal, and each of them will generate one feature vector. What we will use today is so-called DCT blocks. You have seen that figure before, where we generate or split our image into small blocks, and each of these blocks we compute DCT features and treat them as independent observation of this face. And we model the face by the distribution of these features. Okay. The theory is based on Gaussian distributions. So when we have a normal Gaussian function, that's relatively simple. So you have your 2 parameters, which is the mean and the variance of the Gaussian. And you compute the probability that point X was generated by this Gaussian by this function, which probably everyone knows. And the parameters of the Gaussian, like mu and sigma, they are, for a single Gaussian, they are relatively easy to estimate. Given a data set, you compute just the average and the standard deviation. That's relatively simple. When we do that for multivariate Gaussians, this is basically exactly the same. It's just that your input vectors are multidimensional. So you have a multidimensional input R, your mean is multidimensional, and your covariance matrix is, now it's a matrix, it's not only a single value, but it's, in the covariance matrix includes the rotation and the shape of the Gaussian. And estimating these parameters is exactly the same as for one-dimensional. It's just multidimensional. So the mean is just the average of the features. And the covariance matrix is you subtract the mean and transpose, multiply that with its transpose and sum that up. So this can be done analytically. There is no problem with that. Now, when we have a Gaussian mixture model, this gets a little bit more complicated, because now we have multivariate Gaussians, but the Gaussian mixture model is a weighted sum of these Gaussians. So for each Gaussian, we have the mean, the standard deviation, or the covariance matrix, and a weight. And so the weights generally sum up to 1, so that you get a proper probability model. Yes, and the covariance matrix, the sigma here, can be either a full matrix or just a diagonal matrix when you do not want to have independence of, or when you assume independence of the signals or the elements in the vector. Okay, and an example would look like that you have like 3 Gaussian distributions, so in 2 dimensions, and they just sum up to 1. So here you don't actually have a Gaussian anymore, but since you have the overlap of 2 others, the probability is still relatively high. Okay, so now, as I said, it's not that simple anymore to estimate the parameters of the GMM. So what we do is we get an EM algorithm that maximizes the likelihood of a given feature set, of the parameters given the data set. And yes, I think that's enough for this slide. And the idea is that you do that in a 2-step process. So first you estimate, so after initializing your parameters to some value, and I will come to that soon, we do an iterative step where you have an E step, an estimation, and an M step, a maximization step. And for a Gaussian mixture model, this in the E step, you compute the probability for each, you compute the relevance of each sample in your training set to each component of your GMM. So how much does this sample influence the current GMM, the current Gaussian inside the GMM? And in the M step, you estimate the new Gaussian parameters based on the estimated relevances. And then you iterate that and recompute the, until your likelihood doesn't change much anymore. So that's the idea. These are some implementation details. So the E step is, as I said, you estimate the relevances, which is, so for each point in the in your data set, you estimate, you compute the importance of this, so the probability that this point is covered by that GMM, by that Gaussian in the GMM, divided by the total sum of all the Gaussians. And then you say, okay, how high is the relevance of this one point to this given Gaussian? And in the M step, you use the relevances, you update the weights, you update the means, and you update the covariance matrix by using the estimated relevance from the E step. And the nice thing about that is that you can parallelize the E step over the training set. So that's very easy, and that's what we have implemented. And the idea is that you load the Gaussian mixture model from the previous step. You compute the relevances. And then you pre-compute weights, means, and variances. So that's how we have implemented that, so that you can, in the M step, just sum them up. So in fact, these kinds of sums are pre-computed, or the elements inside the sums are pre-computed in the E step, in the parallelization for the E step, and they are stored into what we call GMM stats, GMM statistics. And the M step is basically loading the GMM statistics of all the parallel steps, aggregating weights, means, and variances, and store the new GMM model. So in one step, we load an old model, and we store a new model. That's basically what we are doing. Okay, there are some points about how to use GMMs or practical considerations to use GMMs in biometric recognition. So what I have skipped right now is the initialization. So which weights or which means and variances do we actually use as the initial values for the GMM. And you can use some random values inside, but this is very slow, so then it doesn't converge that fast, and it's also unreliable. What people do instead is they use k-means clustering and use the result, the means of the k-means clustering, to initialize the GMM. And again, k-means is an EM algorithm which does not, which clusters the input data into a given number of clusters. So since we know how many Gaussians we want to have in our Gaussian mixture model, we can just say, okay, we use that as k, and we iterate. So we initialize that we take random data points as our initial centers, and then we assign each data point to the nearest cluster and compute the new mean from the cluster. And that's very simple, and we do that until the clusters don't change anymore. And I have a small example here, a two-dimensional. We have a data distribution like that. We have two initial points that are randomly initialized.
Are the number of Gaussians equal to the number of subjects, unique subjects?
No. And then you do the first E step, where you assign the data to the closest cluster center. And then you take an M step, which moves your center to the actual mean of your data points. And you iterate that. You assign new clusters. You shift your means again. You assign new clusters. And at a certain point, the clusters don't change anymore. And that's when you stop. Practically, you usually stop after a couple of iterations. So in this two-dimensional example, it's very fast to converge, but in higher dimensions, it's a little bit more complicated. So usually you either stop after a certain number of iterations or after some criterion is below threshold. Okay. The next problem is that we have during enrollment, we usually have only few features. In our example, we have features from 5 images. That's not enough to estimate a full Gaussian mixture model. So, and when we ignore the small sample size problem, we basically overfit to the training data, or to the enrollment data in this case. What is done instead is we compute a so-called universal background model, where we compute the cluster, the GMM on top of the training set, which have different identities than in the enrollment set. And then for each model, we adapt the enrollment data of this particular identity. So we adapt the UBM to this particular identity using how is it called? Maximum a posteriori adaptation. So, as I said, we use the features from the training set and adapt that. So, this is basically a picture, or a graph from Reynolds et al. That they have produced in 2000, and this is on speaker recognition data. As I said, most of the GMM algorithms are used in speaker recognition. And I think I'm going to skip this. And finally, to compute the score between a model and a probe, one could rely on the probability that that the probe features belong to the model. But a more more interesting idea is, since we have two models, which is the UBM and the adapted GMM, we can use both. So what we do is we compute the log likelihood ratio using the model and the UBM. And this is basically, we iterate over the probe features and compute the probability that the model, the enrolled model, can, or that these features were generated by the enrolled model or by the UBM, and divide that by the UBM. So the interesting part of that is that this concentrates on client-specific features. For example, if an identity has a scar somewhere in the face, then this scar is very specific, which can be explained by the model of the client, but not by the background model. On the other hand, it ignores features that are common between identities. So it really, because they can be explained by both, and then you have a zero or divide the probability by itself. So it will not add anything. And finally, it ignores features from the background or from occlusions. So this is an algorithm that is by design occlusion invariant, because it ignores the features, because these features cannot be explained by either the model or the background. So again, there you get a log 1, which is 0. And one interesting thing is that this, the denominator can be pre-computed. So that's something that needs to be computed only once per probe. And that's something where we abuse the projection step to pre-compute that. OK. How we have implemented that in Bob Bio. We have the Bob Bio GMM algorithm. We define the parameters in the init function. We compute the UBM using the train projector function. We pre-compute this probability of the UBM in the project function. We compute the client-specific model in the enrollment function, and we compute the log likelihood ratio in the scoring function. Yes, and the UBM computation is, as I said, we use the k-means first, and then this iterative EM for the UBM. And we have parallelized this UBM training, where we have parallelized the E-step for k-means and for GMM. For that, we have generated a specific command line, which is verify_gmm.py, that will only work on a GMM-based algorithm, so that you can use this parallelization. You can also use this algorithm with the verify.py, but then it won't parallelize the training. OK, some time for hands-on. Before that, I have to tell you how we did the parallelization. We have implemented that with grid decay. So the idea of grid decay is that you monitor jobs that are submitted to a SunGrid engine. Because at EDUP they have a SunGrid engine, so where they distribute jobs between different machines. And the idea is that you submit these jobs with the verify.py, and then you have this job manager grid decay to actually monitor what is going on. But since not everyone has an SGE at home, but maybe a multiprocessor system, I have implemented a local scheduler, which can run some of the parts on the local machine in parallel. And verify.py, when you use the parallel option, it will submit and execute these jobs locally. There are some commands that you can use to monitor the parallelization, so the job manager actually, which is jman list will list the jobs that are submitted. And you can also list parallel jobs with, so J is the job index, which usually starts at 1 when you submit the first one. And then if you say -A, then it will also show you the parallel jobs, and it will show you what is currently executed and so on. You can check the logs of the processes by saying JMM report, again with the job name. And these jobs are stored in a database, an SQL database. So when you say JMM del or delete, then you delete these jobs so that the database doesn't run over. Okay, in our hands-on, as I said before, we will use the DCT blocks features. And we use the GMM algorithm. Now, before we have only used like resources that are defined in other packages. Here we now instantiate an object of the GMM class to actually do the computation. And I think I have generated some reasonable parameters in here because the default parameters, so you can use the resource, but for this small example, it will take a long time because we have optimized the parameters on larger data sets so that they generate good results. But yes. So this is the algorithm. We use 20 Gaussians, which is actually the same as the number of identities, now that you tell me, but it doesn't need to be. And we do 5 iterations of k-means EM training and 5 iterations of GMM EM training. So we use the same database, AT&T. We use a 10 tricks preprocessor because we have found that this works very well with the DCT blocks. And as an algorithm, we use the Gaussian Mixture Model. Okay, and again, as before, we write a new configuration file. We say source activate Bob and verify py AT&T GMM dot py minus parallel 4, and then it will run in 4 parallel jobs. And there are some basic experiments that I want to do on that to play a little bit with the parameters. So you compare a different number of Gaussians, you compare different numbers of training iterations. So with the warning that the more Gaussians you use, the more memory is required. And the more training iterations you use, the more time is required. And some advanced experiments is to use different feature parameters, like not the default DCT blocks, but to try to get a higher overlap, lower overlap, or something like that. Change the photometric enhancement, change the image resolution, which requires to write a new preprocessor, or instantiate a new preprocessor, I have to say. And you can try out some of the ISV or JFA extensions. And this should be around what is expected. So the GMM with the base configuration that I have provided will generate this orange line. And then you have a good parameterization that will generate this green one. And it might get even higher than that. So that's what I have just tried out. Okay. So good luck. And I'm here for questions.